So let's consider an example of a pig program and see how expressing the program in terms of these high-level operations offers optimization opportunities that the system can exercise unilaterally without the programmer having to specify it. Okay. So in this example, we're looking at traffic, weblog traffic data with sort of 3 columns here: the IP address, the time, and the URL being accessed. Okay. And so in the first step, we load the data, and here we don't need to use the using clause to specify our own parsing function because presumably the traffic.dat is in some format that pig already natively knows how to parse, so some sort of simple delimited format. Okay, so it's expecting to find 3 columns, and if it doesn't, it'll be an error. All right. So the second command is group, so we group A by IP address. And then third, we say, well, for each of those grouped tuples, I just want the IP address and I want the number of weblog entries associated with that IP address. Okay. So this is counting the number of accesses by particular IP address out there on the internet coming in. Okay. And the next step, well, maybe in this particular task, we're only interested in sort of looking at traffic that originated from 2 particular gateways on our local network, and so we filter for just those IP addresses with the filter command. And then we store the result into a file on HDFS. And so the observation here is that, if you look at this carefully, you can see that as written, this is somewhat inefficient, right? We load a very large data set, we apply a grouping operation to a very large data set, we do some manipulation of those groups across the very large data set, and then we filter it down to something that's much smaller because we're only interested in these 2 IP addresses. Okay. So what would be nice is if we could apply the filter first. And so one thing you could do is just rewrite this program, and in this case, that's probably reasonable. You could probably notice that this was going on and rewrite it yourself manually. But in a more complicated program, you may or may not. And this is not the only example of an optimization that can be done. Okay. And so what Pig will do is actually move the filter automatically beforehand, before the group, and use, I guess I didn't modify the program here. I modified the abstract plan. It won't actually produce the text here. The ASCII is done. Remember we talked about an execution plan, and then it'll manipulate that. And so it moves the filter beforehand because it knows it's safe to do so. And this is, again, I keep coming back to this, but this is the the one advantage of a high-level language might be that it's easier to express your program in. But that may or may not be true. In many cases, it could be actually harder to express your program in terms of these, limited operators. So, you might prefer kind of a general, a Java programmer might prefer a full-width Java interface where they can just write whatever code they want. But the point is that if you can, tie one arm behind your back and express your task in terms of these operations, the system can take over and make manipulations that it would be very difficult for it to do if you wrote in a lower level language. Okay. Fine. So the other point to make here is that, remember, this is what we call lazy evaluation. So when this command is executed, that's when it makes that's when it has an opportunity to apply these optimizations, right? So it did nothing but sort of build up your execution plan as you were executing these commands. It didn't actually do any work. And then finally, when you say, okay, now I really want the result, it can say, aha, I see your list of sequences, or sorry, I see your sequence of commands. I'm going to do some manipulation of those to figure out the right way to execute these commands before I produce the result. Okay. Fine. So we're not done. We now have to map this abstract execution plan down into a sequence of MapReduce jobs. And so the way it does this is it first identifies all the group and co-group operators in the plan and assigns an individual MapReduce job to each one of those operators. And then incrementally what it's going to try to do is walk forward and backward and put as much work as it can into the same MapReduce job. Okay, so the group command needs to be its own MapReduce job because it's going to shuffle things across the network. But filtering, I could apply the filtering condition as I'm loading data off of disk, or as I process a tuple. I can check its condition to make sure it's from one of these IP addresses before I actually apply the group. So I might as well do that in the same MapReduce job. I don't need a whole independent MapReduce job just to do that. Further, the load command is just reading things off disk. It doesn't actually do anything difficult at all. I can put that on the same MapReduce job as well. And so it ends up with this one map function that's going to look something like, as you process a value, it's going to say, parse the data and then it's going to say if val.ip equals this, or val.ip equals this, then emit IP val, or val.ip val. Right, so this little program essentially gets generated by the compiler as just one map function, and then gets executed. And on the reduce side, you can do a couple things. You can construct the groups, but you don't actually care about the groups because you're immediately going to count the results. And so it's smart enough to see that group plus for each is really going to just produce tuples like this, IP and count, and not IP plus some big group. And that's actually pretty significant savings, because constructing these objects and sort of passing them around is pretty expensive. So you don't actually need them. You don't want to use them. So there's sort of two levels of optimization here. One is it moves operators around, which I like. So you got this algebraic flavor. And two, it compresses logical operations into single physical operations. And the overall name of the game here is to reduce the total number of MapReduce jobs being executed, because they're expensive. Okay. And then finally you can write the things out, and that can also happen in the same reduce phase. So this entire task ends up being just one MapReduce job. In other cases, you may need to just do sort of multiple groupings, or you may need to sort, or so on, and each one of those requires its own MapReduce job. So for example, certain commands always require MapReduce job, like sorting. Okay. So what did we talk about in the last several segments? Well, we described NoSQL systems and argued that they're important for a data scientist to understand, in part because you may be using them, but also because you may be asked to weigh in on their relative strengths and weaknesses compared to other systems. And so we talked about NoSQL sort of meaning no schema and no transactions and no language, and maybe less specifically about SQL. And overall, they're kind of a reboot of data systems, zeroing in on just high throughput reads and writes. Okay. Right. And so now the design space of these large scale data systems is sort of being more fully explored with different permutations and combinations of particular features. But overall, there's a clear trend back toward reintroducing schemas and transactions and languages and so on. And so we talked about Google's Spanner system as an example of this trend. So the NoSQL is not, it's an evolving sort of concept. The main thing to realize is that the entire space of possibilities in large-scale data systems is being explored, and NoSQL represents one segment, relational databases represent another, and there's new segments emerging. So you might hear the term NewSQL, for example, which is kind of a re-architected database that does try to achieve some of these other features. Okay. So fine. Then we talked about Pig in particular as an example, not so much of a NoSQL system, but as a analytic system that puts a layer on top of MapReduce. And we chose Pig because it has this relational algebra-like layer on top of Hadoop. And so I want to make the point that relational algebra comes up in a lot of different contexts. And in this one it's a little bit interesting, because although it has a clear relational algebra flavor, it's not actually a pure relational data model. You got these sort of nested structures. And the point here is that you can kind of cherry pick some of these concepts and techniques pioneered by databases, and you don't necessarily have to use them in the context of databases. So you don't need to sort of throw the baby out with the bathwater if a database doesn't appear to be meeting your needs, and these systems are sort of doing that. So as you review different systems emerging as a data scientist, you can start to understand the particular set of features they offer, and understand the provenance of those features and the history there, and the pros and cons therein. Okay. And so Pig also, one takeaway of it is that it has this sort of schema on read flavor rather than schema on write, meaning that you can work with in situ data. Okay, and I mentioned this a couple of times. I just wanted to point out that that's really one of the new requirements associated with maybe NoSQL, as well as even SQL-like systems, is that you have to be able to work with data in its kind of native format. And the reason for that is it's just too big to transform all over the place. All right.